Hello everyone, my name is Arthur and I will introduce our work Covariance-free partial squares and Incremental Dimensionality reduction method. This is our work jointly with Michael Lee, Vitor de Mello and William Schwartz. Okay, dimensionality reduction plays a role in pattern recognition since it's able to reduce the computational cost and produce discriminative representations as well. The idea behind dimensionality reduction is to project a high-dimensional feature space onto a low-dimensional feature space. In this context, partial squares have presented remarkable results since it is discriminative and can operate as a feature selection technique. Despite this, PLS is unfeasible for large datasets because it requires all data from the high-dimensional space to be in memory in advance. To handle this problem, many works have proposed incremental versions of PLS, where the idea is to find the low-dimensional space using a single data of the high-dimensional space at a time. Unfortunately, most incremental PLS methods are ineffective and do not preserve the fundamental properties of PLS. Motivated by this, we propose a novel incremental PLS named Covariance-free Incremental PLS, CIPLS. Now I will introduce our method. Our goal is to find a projection matrix W that project this high-dimensional feature space onto a low-dimensional feature space, but we want to find the projection matrix using a single sample of the high-dimensional feature space at a time. Also, we want to preserve the maximum covariance between the samples and the labels across all components of the low-dimensional space, which is the fundamental property of the traditional PLS. On left, we have the traditional PLS algorithm, and in right we have our incremental PLS. Our main contribution is to extend this decomposition proposed in 2014 to the X and Y loading matrix estimation. In this way, we can compute all steps of PLS in an incremental manner, which means using a single sample at a time. And most importantly, we can preserve this property of PLS across all components, which ensures the maximum covariance between the samples and the labels. Now I will introduce our experiments. Our first experiment compares the proposed method with other incremental PLS and the traditional PLS as well. In this column we have the accuracy, where the higher the better, and in the last column we have the difference in accuracy between these methods to the traditional PLS algorithm, where the lower the better. We can see that our method achieves the lower difference compared to the traditional PLS. In particular, our results were statistically equivalent to the traditional PLS. We observed the same trending in the YouTube Faces and ImageNet datasets. In terms of computational cost, our method is more efficient than other techniques. For example, this figure shows the time for estimating the projection matrix, where we can see that our method is the fastest incremental PLS. In this work, we demonstrate that it's possible to compute all components of PLS incrementally using simple algebraic decomposition, thus enabling its applicability on large datasets while preserving its properties. Our method is more accurate and faster than other incremental PLS methods. The source code is available at this link. Okay, and that's all. I hope to see you in our paper session.